Ladies and gentlemen, I have the pleasure and the honor to welcome you to the third webinar in the series, Scientists Empowering Scientists. Good morning to most of you, good afternoon to quite a few of you in Europe. We will have a repeat of this webinar next week, next Tuesday at 7 p.m. Pacific time for the Asian time zones or the ones on the American West Coast who are a little later risers. The title of today's webinar is Time for Paradigm Change. We will give you an overview of the new IPA integrated patch amplifier and the SutterPatch software. Let me introduce one of the speakers, Telly Galiatsatos. He graduated at Queens College, New York in computer science in 1987 and joined Instrutech the same year, started in IT engineering support and eventually became the hacker product specialist and the general manager. In 2007, when Instrutech was acquired by Hacker Instruments, he became the general manager of Hacker Instruments, which is the US division of Hacker Electronic. And since 2015, I have the honor to call Telly my colleague again. Today he works in technical support and product development.
Thank you, Jan. My turn to introduce you. So the other presenter today's webinar is Jan Dolzer. Jan graduated from Philipps University in Marburg, Germany. He got his doctorate in electrophysiology, and he did his research on insect sensilla. In 2003, he joined Axon Instruments and survived a number of corporate changeovers there, and as product manager for Patch Express and conventional electrophysiology. In 2011-2012, he joined Sutter Instruments, where he was the product manager for the laser-based micropipette pullers. In 2012-2014, he joined Hacker Electronic as Vice President of Sales and Marketing, and as you can guess, that's where Jan and I became colleagues for the first time. And since 2014, he returned to Sutter Instrument as the product manager for the patch clamp systems, which we're going to be discussing today. So with that, I'd like to pass the ball back to Jan. He could start our webinar.
Okay, let's take a quick look at the agenda today. We're going to give you a quick introduction, 2-3 housekeeping slides, mostly about how to get audio. Doesn't seem to be as much of an issue anymore as it was. I will show 1 or 2 slides about the existing Sutter Instrument product lines and then answer the question why we built a wholesale patch clamp amplifier. Then Telly will give you a conceptual overview over the IPA integrated patch amplifier, the hardware of the system. And most of the talk today will focus on the SutterPatch software. We will start off with a conceptual overview and then give you a few feature highlights. We don't want to keep you busy for the next 15 hours, so we're not going to go into all corners of the software, but highlight a couple features. And then hopefully we will have a lot of questions that we can answer or have a discussion. At the end of the webinar, you'll be guided to a quick survey. We kept it very short. This is mostly about how useful you found the webinar today, how the timing worked, feedback for us that shows us what can we do best to help you going forward to meet your needs. You also have a field where you can suggest topics for future webinars, etc., etc. So please take the time to give us your feedback. Hey, you did a great job here, or that was a complete waste of my time. How can you get audio? Audio is transmitted over your internet connection, and it seems like there are a few questions along the lines of how do I get audio? You can turn up the volume of your computer if your computer is not equipped with speakers, or if you don't hear me now, then you don't hear me now. The dial-in numbers are on the control panel on the right of your screen by default. There's also international numbers. Used to be the most frequently asked question in webinars, but seems like most computers have voice over IP these days. Talking about questions, the session control panel on your right also has a Q&A section. You can type your questions there, and all questions will be addressed either during the Q&A session at the end of this webinar, or the ones that we don't get to, we will address offline by email. All questions will be answered. We have documentation materials. We have a PDF file of the presentation slides, again, that can be downloaded in the handout section of your webinar control panel. It's not the ones shown here. That was from the previous webinar. And also a recording of this webinar will be available on our YouTube channel, probably within the next 2 weeks. As I said, we're going to have a repeat session of this webinar a week from now, and we will combine the Q&A sessions from both webinars into one recording. And you will find that on our YouTube channel at this web address, together with a lot of other useful videos. And everybody who registered for this webinar will be notified that the recordings are available by email. Now to the webinar proper, talking about the product portfolio. Why did we decide to make a wholesale patch clamp amplifier? There's actually two parts to this question. One is, why did we decide to make a patch clamp amplifier? And the second part is, why did we decide to make it a wholesale patch clamp amplifier? Let's take a look at the existing product lines that Sutter Instrument made. We are market leader in instrumentation for micropipette fabrication. You know that as pipette pullers mostly, but we also have glass and accessories. We have a number of micromanipulators that many of you use for their patch clamp experiments. We have imaging equipment. We make microscopes like the SOM and the MOM. We recently added instrumentation for noise isolation, that is electrical and mechanical noise. You may have seen that in the loop that ran before the webinar started. We have air tables and Faraday cages now. We make microinjection equipment and last but not least OEM products. Except for the last two, almost everything here can be used in combination with a patch clamp rig. And the only thing we did not make was patch clamp systems. That's why we decided to make a patch clamp amplifier with a digitizer and acquisition system, because we believe only if you have the full system, including the software and everything, that there's going to be acceptance in the marketplace. Now, why did we decide to make it a wholesale amplifier? Let me step back a little bit, and this is probably known to most of you, to the patch clamp configurations, and many of you may know this picture. I stole this from Bertil Hilly. Once you've formed the seal, you're in the cell attached configuration, and what you see are single channel currents. When you withdraw the pipette from here, you're in inside out, and of course you also see single channel currents. Now you can control the voltage over the membrane. Then if you destroy the patch that spans the orifice of the pipette, you see wholesale currents. And I'm pretty sure, looking at the audience, most of you, if I wake you up in the middle of the night and show you something like this, you will instantly say this is a sodium current, wholesale current. And for completion, if you withdraw the pipette from this configuration, of course, you're in the outside-out configuration. Now, talking to many people who do patch clamp and asking them, what do you do? Almost everybody said, well, actually, most of the time what I do is really wholesale recordings. I occasionally may do single channel recordings, but wholesale recordings is what I do most of the time. And that's why we decided to make our first patch clamp amplifier a wholesale amplifier. Admittedly, it's a little easier than a single channel amplifier too, because the requirements in terms of noise performance are not quite that dramatic. And in the next couple slides, Telly will introduce you to the IPA patch clamp amplifier and give you an overview over its features and capabilities.
Okay, so here it is. This is what the IPA integrated patch clamp amplifier is, and you see it's a nice slick 1U height device, so we know the rack space is a premium in most labs, and as you see from the front panel, the only control that we have on there really is just the power switch. So let's go into it a little bit of some of the highlights and features of the IPA. It is a fully integrated patch clamp amplifier with a built-in data acquisition system, and by that I mean it's actually a single board solution. Both the amplifier and the data acquisition interface are one board, not just different components that are put inside a chassis. So this allows for very simple setup, since the only thing you really need to connect is the head stage on the front panel and the USB connection on the rear to your computer. So the IPA supports both wholesale voltage and current clamp experiments, And it could also be used either as a bundled system, and by bundled I mean with our SutterPatch software, or it can be used as a standalone amplifier on existing recording setups. So if you already have a digitizer and software that you currently use and you want to evaluate the IPA, you could easily do that. And that's when you would be using the front panel BNCs to actually make those connections. So you have the connection for command in, and then of course you have for the current and the voltage monitor. So let's go a little bit now into some of the feature set for the IPA. Some typical applications that the IPA supports is tissue slice recordings, cultured cell experiments, in vivo patch clamp, network studies, cell line studies from adherent or dispersed cells, and optogenetics. Now this is not a complete list by all means, but just an overview of some of the applications. Now let's go into some of the featured highlights of the hardware itself. So in voltage clamp mode, it's optimized for wholesale patch clamp, as Jan mentioned earlier. It uses a resistor feedback head stage with a 500 megohm feedback resistor. Open circuit noise is about 1.4 picoamps in a 0.1 to 10 kilohertz bandwidth, measured with an 8-pole Bessel response filter. The range is plus or minus 20 nanoamps. And this gives us a resolution about 5 femtoamps to half a picoamp. We have both automatic and manual capacitance compensation supported in the IPA. We have electrode compensation up to 25 picofarads, and cell compensation with a membrane capacitance from 1 to 100 picofarads and a series resistance from 1 to 100 megohms. The IPA also supports series resistance prediction and correction from 0 to 100%. And by prediction, some of you may know it as supercharging. As mentioned earlier, the IPA does support both current clamp and voltage clamp. So let's go into some of the current clamp highlights. So the IPA does support true current clamp. It has a voltage follower circuit built in. We have current injection of plus minus 20 nanoamps. Current clamp bridge compensation and capacitance neutralization. And it also has a tracking feature, which was manual in the olden days, but now you could set your slow holding potential tracking to compensate for drifts during current clamp recordings. Now, another integral part of the IPA is the built-in data acquisition interface. And let's go into some of the feature sets of that. As mentioned earlier, it's an embedded data acquisition system. It has a built-in microcontroller, and this provides intelligence to the unit. And we actually use the microcontroller to handle all of the compensation routines. So none of it is done actually on the host computer, but all done internally in the IPA itself. The IPA provides 6 ADC analog input channels, and they're all 16-bit resolution. 2 of them are hardwired to the amplifier section itself for current and for voltage, and 4 are available for any external signals that you would like to record. Each A-to-D input channel is 50 kilohertz per channel, and all 6 channels can be simultaneously co-phase acquired. What I mean by that is that all channels are acquired on the same clock pulse. The IPA provides 4 analog DAC output channels. Again, they're 16-bit resolution. 1 is physically tied to control the holding potential of the amplifier itself. You have 1 that is specified for the command, for stimulus, and 2 for any kind of external control. 8 digital TTL output channels are provided, and again, this is mostly for controlling external devices, for example, a perfusion system, and you have a dedicated trigger out that goes high when you start acquisition. And data acquisition can be initiated either by a precise microsecond clock internal to the unit or via an external trigger. The IPA system, as I think if you saw the loop, we talk about bundles. So the IPA system itself is a bundle. And what does that bundle include? So each IPA is the IPA amplifier and digitizer. It includes a copy of the SutterPatch software and a license for Igor Pro 7. And the whole thing we have as single unit bundle.
Before I start talking about SutterPatch software, let me also mention that it's the coolest blue amplifier in the known universe. The SutterPatch software is a system that's used for data acquisition, data management, and data analysis. Now, what does data analysis entail? Of course, it's raw measurements like you're measuring peak currents, but then also you want to have derived analysis. In many cases, people want to do things like IC50 curves or conductance voltage relationships, things like that. So more derived analysis procedures. And last not least, you want to have publication quality graphing. And all of that is provided by SutterPatch Software. An important aspect of it was also that it's multi-operating system compatible. You may have noticed that we're using a Mac here to run not only the PowerPoint presentation, but we will go into live demos a little later on Macs, but it works just as well on Windows. SutterPatch software, as Telly already mentioned, is powered by and built on Wavemetrics Igor Pro 7. And let me briefly talk about what the benefits of that are. Benefits of using Igor Pro is that there's already a pretty broad user base among electrophysiologists. Many of you, we know, use Igor Pro to do their data analysis already. There's a wealth of native functionality that we can build upon. Igor Pro is pretty good at data acquisition in many instances, data handling, of course. There's a huge number of data analysis features and also publication quality graphing. Many of you prepare their graphs using Igor Pro. There's a very well-documented programming interface, but our goal was allowing those of you who do not do any programming and do not want to do any programming to get everything done as well. The file format is compatible with many existing analysis procedures. And last not least, the guys at Wavemetrics are absolutely stellar when it comes to tech support. Let me take you through a couple components of the program. Let's start with the scope window. We put a lot of emphasis on creating a visualization of the data. The scope window, the first and foremost component in the software that you're looking at, comes in multiple flavors. And to do this, I need to switch computers real quick. Okay, I want to show my screen. When you start up SutterPatch, you are first presented with the dashboard. And one of the flavors that the scope window comes with is the membrane test. So what you run here is simply a step pulse, and then you can be in bath, in seal, or in cell configurations, can write the values, etc., etc. The next flavor is the data acquisition scope window, and we'll get to this screen later on. This obviously runs in demo mode, so this is just a simulated passive ohmic response. Simple IV step routine. And you see the real-time analysis here already. Again, we'll get to that in a little more detail later on. And the third flavor that the scope window comes with is the reanalysis window. And let's take a quick look here. This is an example of a data set. This is extracellularly recorded action potentials from an insect syncyllum. You may remember from my bio that Telly introduced in the beginning of this webinar. I worked on insect syncylla, so guess who this data is from. Each of these sweeps represents the average of a 10-minute recording in olfactory syncylla in a moth. And what that means is if you change the view to a time course, to a continuous time course, you would have to zoom in very far to see something meaningful with a 12.5 millisecond sweep and then 10 minutes of nothing in between. So most conveniently, you can take a look at the concatenated view, and here you see the waveform, the individual action potentials. You already seen you can zoom in by dragging along the axis, for example. That is something that we put a lot of emphasis on, being able to scale, to zoom in, to zoom out, to navigate through your data. You have the overview navigator here that shows you where in the context of the total file you are, and also allows you to move to a different place in the file. And one thing that we are pretty proud of is the three-dimensional view, three-dimensional representation of the data. What we see here is the way the waveform changes over the course of the sweep number. 56 sweeps, 10 minutes each. These are almost 10 hours of a recording. And what we did here was applying a drug at where it says stim start here, where the tag says stim start, applying a drug, and then something changes, the waveform changes. The peak-to-peak amplitude gets bigger, and then gets reduced a little bit, then gets bigger again. But what you would not see unless you have the opportunity to rotate this and look at it from different angles is how the repolarizing phase here gets extended too, while the peak-to-peak amplitude is at its biggest. And that gets reduced again a little bit. And based on these data, I postulated back in the day that the drug that we applied here affects two different types of ion channels. Non-specific cation channels that affect the peak-to-peak amplitude, and delayed rectifier potassium channels that affect the repolarizing phase. Sure enough, that has since been shown. This is data that's almost 20 years old. This has been shown in patch clamp experiments since then and has been published. Once you know what all this means, top-down view like this, a heat map would actually be enough of a representation. But if you don't know what parameter you want to analyze, the ability to rotate this is very useful. So in assay development, this gives you a lot of extra capability. That concludes the live demo at this point. So let me switch back to the PowerPoint presentation again. Telly's going to continue talking about the amplifier control panel, how to set and to monitor all the amplifier parameters.
As we've shown earlier, the IPA has no controls on the front panel except for the power switch. So how do we have access to all of the settings? For that, we designed the IPA control panel. So this is a virtual front panel for the amplifier itself. So let's go a little bit into how it's broken up. First, let's start off at the very top. You have where you monitor and you set your mode. For example, switch between current clamp and voltage clamp. As you go down, we have the controls for setting the different tabs. And by tabs, I mean the different sections depending on which mode you're in. In your voltage clamp, you have one set of controls active. In current clamp, you have another set of controls. And finally, in the I/O, you have control of the digital channels and our auxiliary inputs and outputs. Further down, you have where we set our holding, our electrode compensation, our cell compensation, and RS correction. And then as you go all the way down, we have our gain and filter settings. Now switch over when we're in current clamp mode. We now have the middle tab position activated. So now we have slightly modified controls that are only accessible in current clamp. So again, you have electrode compensation, your bridge balance, and your tracking, as well as gain and filter settings. And the final tab is the I/O control. And this is where you can set and read asynchronous digital outputs and both the A to D and the D to A channels. So for the digital outputs, you could actually set one of the 8 digital bits or all 8 of the digital bits to control external devices, like I mentioned earlier, a perfusion system. And the same should be true for reading a single value on an A to D channel. For example, something like a temperature from a temperature controller, and setting a DAC to also drive some kind of external device. Now we have, that's the main control for the amplifier, so we get all that prepared. Now we need to actually do the acquisition. And acquisition in SutterPatch is handled through the routines. So first, what is a routine? Well, the Merriam and Webster website, I was going to say dictionary, but nobody uses a dictionary anymore, says that it's a regular way of doing things in a particular order or a sequence of computer instructions for performing a particular task. The SutterPatch definition is a set of data acquisition and online data analysis parameters that controls input and output channel timing, triggering, command waveforms, leak subtraction, and display. You see, it's quite a mouthful. So now, how do we access these routines? How do we manage these routines in SutterPatch? Well, we have a main panel and some sub-windows for setting all of the different controls. So let's first go over a little bit of what the main panel looks like. First, you have on the left-hand side the routine pools. And what is a routine pool? You could have any number of routines that you've pre-programmed and created and stored in a single file, which we call a routine pool. And here you have your list of all the routines in your pool, as well as all the controls for manipulating them, like renaming, duplicating, and so forth. On the right-hand side, you have the individual settings for the active routine. So here's where you have all the properties like the channel settings, the parameter settings, real-time measurements, and so forth, and I'll go into a little bit of that into the next slide. And finally, on the bottom, we have our routine preview, and this is a great tool. It updates automatically as you're creating your routine. So as you're designing your waveform, you can get a real-time representation of what it will look like, including the regions of interest for your measurements. Now, there's a special mode that allows you to show the time course, which is similar to what Jan showed with the oscilloscope window. And this in particular is quite helpful when you're running our continuous sweep mode, where some of you may know it as a gap-free acquisition. And here you could see the same 10 sweeps with an incremental amplitude shown from the beginning of sweep 1 all the way up to sweep 10, and it shows you the time base for the entire series acquisition. Now let's go a little bit into the routine editor components or the sections of it. So in the routine settings, you have the options and controls for going through all of the different windows to specify the different settings. So for example, let's get started with the acquisition and routine parameters, and here you define the general acquisition parameters. Things like the type of acquisition mode, the sample interval, sweep start time, and so forth. Then you go into the input channels, and here you could activate and deactivate what inputs you would like to use from the IPA, as well as the individual components or variables for these channels. Then you go into the output channels in the waveform, and this is where you generate your outputs. You have the same set of controls as the input channels, where you could specify what channels to activate, including both the analog D to A channels as well as the digital. You could also enable P over N leak subtraction pulses for each of the D to A channels, and then you can go in and actually edit the waveform. And this is a segment-based waveform generator, which allows you to create very complex stimulation patterns, and then again, that's for each of the D to A outputs as well as the digital. And then finally, to put it all together, when a routine executes, you have some real-time measurements and analysis that you would like to perform. So here in the routine editor, you could specify what type of analysis you would like to do, what your measurement regions are going to be, and which X and Y graphs, which measurements would you like to plot against which. As mentioned, our routine pool that we supply with SutterPatch has a number of different examples, and this is great because you can use these as templates to design your own. It's easier to modify one than to start from scratch. So we supply some routines, for example, like for sodium channels and IV. And here, this is what it would look like in your preview. When you execute the routine itself, you would get acquired data on your oscilloscope window. With the measurements activated, it will do the real-time analysis measurements with each sweep that's acquired, and also display it in a separate window next to the oscilloscope. And I'll show you how this actually executes shortly. So we have, as I mentioned, a few other examples that we provide. Again, for sodium channels, steady state inactivation. And I won't go into details of the parameters, just some of the examples. We have, for sodium channels, again, slow inactivation and recovery. And these are just previews of the routines that exist. And another example is for synaptic stimulation, and this one's slightly different. The acquisition here is quite straightforward. It is a single pulse, but you have a lot more measurements enabled for doing your real-time analysis. Talking about routines and creating a routine, over the years, many people have come up to me and brought me a figure or send me an email, say, okay, well, this is what I want to do. Can you help me dissect and create this routine? We could do that by first we look at the figures here, and we can get some quick ideas of what's going on right from the figure. So we know here that we have a holding potential of -95. We see here that we start from -65, and we have an amplitude increment that finishes at +5 millivolts. And then we have to look at the actual paper to get some timing information, some more information. So in this case, this is from a paper from Randall. We found out in the literature that you have time base was 25 milliseconds for the test pulses, and the sweep duration was 5 seconds. So what parameters do we need to make this routine work? And here's how it's done. So first, we go to the dashboard, as Jan showed earlier. We'll go into the routine editor. We look at our routine pool and say, okay, let's find one that's similar. So in this case, I have an example IV. And let's go in and change some of the parameters. So first, we'll make a duplicate of that. It comes up with an automatic name with just a numbering scheme, but you could change that name to whatever you like. For example, IV webinars, I did here. Then you could put in a comment, and this is descriptive text that is stored along with routine. And this is a great idea, so later on you know some ideas of what you have done. Then let's go in and change some of the parameters. So here, we saw that we had a sweep start to start time of 5 seconds. So we'll make that change here. And the number of sweeps to accomplish that IV was 8. And we'll leave the rest of the parameters the same. For input channels, there's no change. We're going to be recording the current and the voltage, but we need to change the waveform slightly to match that figure. So we'll go and click on the edit waveform, which brings up the waveform editor. And here we're going to make a change only to the middle segment for our start value and our increment. So our start value was minus 65 millivolts, and the increment was also 10 millivolts, so no change there. We'll do an update, which, as you saw, the cartoon got changed as well. We also have to change the time for that segment to 25 milliseconds instead of 35. Okay, and then we're going to save the pool to store our changes. And then we're going to execute it. Activate actually sends the programming sequence to the hardware. As you can see, the scope window and the analysis window come up, and then we hit start acquisition. It actually executes the routine. On this case, we had each sweep a time base, a start to start time of 5 seconds. So you see that each sweep is taking that long to execute. And for the sake of time, I'll only run through a couple of the sweeps here. I don't know if many of you noticed, but the first and last segment of my waveform included a value for the amplitude that was set to hold. And why do we offer that option, and why do we have it? One is it automatically sets the value when the routine is activated. So if you're changing and playing around with holding potential, you don't have to worry about going in back to the waveform editor to make those changes. It will automatically update as soon as you activate a routine. And there are some other important factors for selecting these segments. So the first segment is set as holding. Then the following information is also stored with a trace. So for a current trace, the leak current, sometimes called the zero current, is stored along with it. And for the voltage trace is the actual holding voltage. So even if you don't have metadata parameters, which Jan will discuss later on, you have some of this information from the trace itself. And same in current clamp mode, you have, again, same thing here, current trace where you have the actual holding voltage, and then for the voltage trace, the actual cell potential for the clamp cell. Now, if the last segment is also set to hold, those traces carry information as well. For example, things like the tail currents. So now I'll switch to the next part where Jan will continue.
Okay, and I will talk about one more routine example about P over N leak subtraction. And that is something that we implemented to be within the sweep as opposed to be invisible in the background. Those of you who use one of the two established software platforms are used to seeing the main sweep, but not seeing the sub-sweeps in P over N leak subtraction. So we found it quite useful to have that within the sweep. We are not limited by sweep duration, legacy, limitations in terms of memory that was available, etc. So we could afford to do that. I want to highlight two aspects of the P over N leak subtraction. One is you can have alternating leak polarity, as is shown in the cartoon here. And the second one is the leak ratio does not need to be the inverse of the number of subsweeps. This is an example of a P over 4 routine. And in this case, the ratio would be 1/4 the amplitude of the main sweep. But we could also make that just 10%, as shown here now, and then scale that up accordingly. So there doesn't need to be a fixed relation. p-over leak subtraction is also occasionally associated with excessive line frequency hum on your signals. And here's something I would like to show you, something that I found that many patch clampers are not aware. How can you both increase or reduce line frequency hum using p-over leak subtraction? And most of us would like to reduce line frequency hum. Intervals, subsweep intervals that are in phase with the line frequency can amplify the hum on your signal. What we see here is a main sweep, and this for simplicity is a p/2, and what we're going to do is add a little bit of line frequency noise, a lot of line frequency noise really, and for simplicity we'll only have the bass frequency, not the harmonics. The resulting signal is the line frequency, the sine wave superimposed on the subsweeps and also on the main sweep, and if we add all this up, what we'll end up with is a signal that has about 3 times the amplitude of the line frequency hum as the original signal, and what we really expect to see would be just a straight line, because everything should, if it's only the signal of interest, everything should cancel each other out. Now, how can we avoid this? By using counterphase sweep-to-sweep intervals, subsweep to subsweep intervals, and also subsweep to main sweep intervals. Same thing here, we have the main sweep to subsweeps. We add our line frequency hum, our sine wave, and the resulting signal looks like this. But now if we add up the subsweeps, what we can imagine is how the line frequency component cancels each other out. And then if we add that to the main sweep, what we end up with is only 1 time the line frequency contribution superimposed on our expected straight line signals with maybe a few short transients here. So all this was done by offsetting the subsweep interval by 10 milliseconds, depending on where in the world you are, or 8/1/3 milliseconds, as opposed to having them in integer multiples of the line frequency interval, I should say. We also implemented that in SutterPatch software so that you can adjust for reduction of the AC line frequency. That's why I'm showing the whole thing. And we're working on auto detection. That's a fairly straightforward algorithm, actually should be implemented sometime soon. Let me switch gears and talk about data structure and the data navigator. For us, it was very important to be able to make sense of the data. Telly already introduced a few of the components. Let's look at the data structure. This is an experiment, and within an experiment, you could run a routine, similar to what Telly showed you before. That could, for example, be an IV routine, a series of steps that you use to generate an IV curve, a sodium IV curve, as in this example. A routine consists of one or multiple signals, input signals, each of which has typically multiple sweeps. In Telly's example, I think it was 8 when he originally started. And then, of course, each signal has all these sweeps. The routine execution in SutterPatch creates a paradigm. Now, once you start a routine, a paradigm is automatically started. What's the purpose of this paradigm? This paradigm allows us to keep track of changes that are made in the course of the experiment later on. Also, other routines that may be started, you can have a lot of routines. So this will be the simplest scenario that many of you are going to start off with. They're going to start running a routine similar to what I did previously also when I showed you the data acquisition scope window, and that would automatically trigger a paradigm in the background. You don't even need to think about it. But then the next step is what we call planned paradigms. That is, you plan your experiment ahead of time, and what you want to do is create a paradigm in which, for example, you run a routine. That could be your sodium IV. You look at the peak current. If the peak current is above a certain threshold that you accept as a quality good criterion, then you go on to the next routine. And then once the cell has passed this, you could determine the half inactivation potential. Here you may want to go on, for example, to a dose response curve or something like that, that you run at the half inactivation potential as the holding potential. And Telly is going to show you a couple more of those paradigms. He's going to go into what is a paradigm to begin with, and then show you how to do these. And then we should have another 10 minutes or so to go to wrap this up with a very brief overview over the metadata, and then go from there. Over to Telly.
All right, so the plant paradigm, what is it? Again, from the Merriam-Webster website, a theory or a group of ideas about how something should be done, made, or thought about. The SutterPatch definition is a sequence of control instructions in an experiment. You could think of it as a simplified programming language where you have a set of steps that you execute to perform an entire experiment. So how do we handle paradigms in SutterPatch? Similar to the routine, we have a paradigm editor. And this, as you could see, very similar look and feel. And again, I will break it down to the different components. We have the paradigm controller. This is where you start, pause routines, set timers, and so forth. Then you go into the left-hand side, the paradigm pool, similar to the routine pool where you have a collection of these paradigms in a single file. And the same type of controls apply here as well. And then on the right-hand side, you actually have the paradigm program, the paradigm steps, where each one of them defines a sequence, something to execute. In this case, what's showing over there is amplifier controls. So for example, instead of using the the IPA control panel, you could be actually setting things like the mode, holding, and so forth directly from a paradigm. So how do we work with paradigms? I'm going to show that in an example. So my example is going to illustrate some of the things that Jan talked about earlier, and we'll show later after this slide. Is first we're going to execute an IV routine, except we're going to do it one sweep at a time. And what that means, for example, is we had 8 sweeps in this IV. Well, it's going to run through them, and after each sweep, it's going to perform some checking to see if it should continue with the acquisition or not. In this case, we are adding an if-then statement where we are checking a variable that we specify, which is P1, and then we're checking if it's minus 200 picoamps, and then we're going to break if that condition occurs. Then we're going to create a for loop, which will execute the routine both 2 times, and then we're going to actually execute the IV routine once again without any of the checking. So how we're going to do that. Here, I have prepared a movie that goes through the steps to do that. Again, we start from the dashboard. We go and we click on paradigms, which brings up the paradigm editor. And the same way as we did with the routine, we're going to take one that has some of the components that we need, where we're going to duplicate it and give it a name and also a description, the same way we did with the routine. And then we're going to go into the actual paradigm steps and start inserting the new commands that we talked about. So here we have the for each sweep already, and it's already set for the IV routine. So now we're going to add components inside that for loop. Here, first one we're going to do is set one of our paradigm user variables to the measurement results that we defined in the routine editor that I showed earlier, which in this case M1. You can use the information, the M1 measurement directly, but I just want to illustrate that we do have these user variables available that you have access to. And then we're going to add an if-then statement where we're going to compare 2 equations. In this case, the equation is the variable P1 on the left-hand side. The operation is greater than, and on the right side is just a value, which is 200 picoamps. Now, if this condition is met, what do we want to do? We actually want to add a break statement in here, and a break comes in 2 flavors. One is to actually break the routine or the paradigm execution steps, or the actual for loop itself. In this case, we're only interested in the for loop. All right, so we did part of the steps we wanted to do. So what I'll do is I'll save it now and execute it just to see that I'm heading in the right direction. So when you start a paradigm, it goes through and executes step by step. So here, it activated the routine IV, it started the acquisition, it brought up a scope window, and then ran the acquisition until it hit the target of the minus 200 picoamps. So now let's add the 2 additional routines that we talked about. So first, we're going to create the for loop, and we're going to add just a counter of 2. Then within that for loop, we're going to perform the routine bow tie. So here we're going to go select the command routine, which also provides us with a list of all the available routines in the current routine pool. So bow tie is right on the bottom there. We'll select that. And then finally, we're going to insert after that the end of the for statement to execute the IV routine by inserting another routine command. Again, routine, and we're going to specify IV, which is the very top of the list. All right, so now we're going to save this and execute this paradigm. And as you can see, when we're executing the paradigm, if the paradigm editor is open, you actually see it go through the steps one at a time as they're being executed. So you see it jumping around, then it jumps to the for loop, it executes the bow tie test twice, and then we go into the IV. Another thing you may have noticed is the color schemes. Some of them look black instead of red, and unfortunately that's the resolution of the movie. It should all be the one color. This now takes us to the next step, which is Data Navigator, which I pass back to Jan.
Like in the cook shows, we already prepared something. I have a very similar paradigm to what Telly just ran, and the way we make sense of the data is the Data Navigator. So what you have here is a tree-like structure of everything that went on in our experiment. And in this case, I ran a paradigm, I called it alternating routines, but it has the same structure as what Telly just showed us. I can look at the IV. In this case, this is the one that Telly ran. It popped out when the current mean exceeded minus 200 picoamps. I can also get an overview over the entire paradigm though. Here is the time course of what actually happened during the entire paradigm. And if we zoom in, we should be seeing this will probably be the bow tie. You see this somewhat odd waveform here, the bow tie waveforms. And again, here on the overview navigator, you see where you are in the context of the experiment. And with a right click, you can look at the individual series. So this is a very powerful tool to navigate through the data. You can click on a sweep to make it the active sweep. One thing we did not discuss really is the VU meters. Here, they show you how your signal utilizes the range of the amplifier. In this case, we would have hit the saturation. So this signal would have clipped the amplifier. This was recorded in demo mode. Telly, I believe, had an actual amplifier connected. I was in demo mode, and that's why this would briefly hit the saturation. One more thing that we can look at here is what's called the metadata. And metadata is information outside the individual samples. Let's look at them by parameter in this case. So for example, we could look at what amplifier model was used for the individual signals here, and both the current and the voltage signal came from an IPA, or what the serial number was. In this case, as I said, this was demo mode. A lot of the information can be automatically determined by the software and is automatically written. But there's also the opportunity for the user to set a number of metadata parameters. For example, if you want to define an identifier for the animal that you use, you could use a particular value, or you could use values that have been used before, or increment identifiers. So for me, every single animal had an ID, and that's how I kept track of where the recording came from. And then you can also decide to be prompted for confirmation before either an experiment, a paradigm, or a routine. You could have information about the tissue, where the organ came from, about the stimulus, like a compound concentration or something like that. And we have a total of 500 metadata parameters that you can define, and not all of them are shown by default. You can set the complexity level, and then you have a lot more control. Here you have, for example, the instrumentation and software, the amplifier. Since most of this is automatically determined right now, there's only so much you can define but for example, for imaging, you could define the image file name or things like that. With that, let me wrap this up. We're almost done. And these are the slides that represent what I just showed you live. The review panel that gives you overview over the entire paradigm, the metadata that keep track of what's going on, defining the metadata, the complexity levels. The live demo we already went over. Last thing I want to mention briefly is the application modules, the two that we already have implemented. Focused functionality. One is the camera module. Igor natively supports operation with a camera. And in this case, what we show here is taking a snapshot of the cell that you're recording from, or some people like having snapshots before and after the recording to see how the cell fared, how viable it still is, or you may want to have Lucifer in the patch pipette to confirm the whole cell configuration, things like that. We do not currently support real-time acquisition of images in sync with the pCLAMP signal, but that is in the pipeline for future versions. And just a snapshot here of the event detection application module that we recently finished. And this is a deconvolution algorithm that's applied here. Event detection obviously is a topic for its own separate tutorial, and I'm going to leave it with that and not go into too much detail. If you have questions about that, we may be able to deal with that a little more during the Q&A session. In the interest of time, let's move ahead, have Telly introduce the team, and then go to the Q&A session.
Okay, so I'd like to introduce the electrophysiology team, or our pCLAMP system team at Sutter. And that would include, first I go over our pCLAMP hardware team members, and that would include Gregory Hempstead from UCSF, Rich Lobel, formerly from Axon Instruments. For many of you who don't know, Rich was the original designer of the Axon 200B amplifier. And finally, Aaron Best from Harvard Medical School. For our SutterPatch software development team, we have Bert Mertz from Axon Instruments and Molecular Devices, Hubert Affolter from Heka Electronics, Gregory Hempstead again from UCSF, Lindsay Dong, who will be our moderator for our question and answer session, and as Jan mentioned, both he and I program as well. Let's go a little bit of a system summary of what we've talked about today. First, we talked about the IPA, integrated pCLAMP amplifier with digitizer, optimized for wholesale and current clamp experiments. We discussed the software, in this case the SutterPatch software that we've developed. It's a data acquisition and analysis package. And our main goal with this software package is to combine advantages of existing platforms and improve on them. And by improve, we mean by getting feedback from customers. And finally, want to reiterate the fact that the IPA is a bundled system. So when you're comparing it with the other systems out there, keep in mind that it does include the amplifier, the head stage, model cell, the pipette holder, built-in digitizer, and software. So other than plugging it into your computer and connecting the head stage and manipulator, you're all set to go with your recording setup. Now I'd like to introduce Lindsay. At the end of our webinar. In 2012, Lindsay got her biomedical engineering degree from Huazhong University of Science and Technology in China. From 2013 to 2015, she was at Cornell University getting her master's in biomedical engineering, where she did her research at the Schaefer and Nishimura lab. And since 2015, she joined Sutter Instruments as a SutterPatch software developer and as a MOM computer system and software specialist. And with that, I'd like to send over our webinar to Lindsay. Thank you.
Okay. Thank you, Telly. Thank you, Jan, for the presentation. Let's look at some questions here. Here's the first one. Currently, we use an external stimulator for complex stimulus patterns. Can we create complex waveforms with SutterPatch?
I'll take that one. Yes, the routine editor provides a number of different ways to create waveforms. So you have the capability on a segment-to-segment level to use steps, ramps, sine waves, chirps, or even a template wave. And what I mean by a template wave is a wave that you generated from an external program or an Igor itself, and you read it in and use that for a stimulus. For example, taking like a recorded action potential and using that as a stimulus itself. Actually, if I go back into live mode, I could show you a little bit of one of the tests that I've done with the amplifier, again, mostly for testing, but it illustrates some of the things that you could do. So what I'll do here is I will initialize the hardware so we can get out of demo mode, and then connecting to the amplifier itself. And then let's see here, we're going to go into our routines, and I have a routine that I've been working with called multi-test, and let's activate it and see how that runs. So here you could do start acquisition, and as you could see here, here I'll have to blow it up a little bit. So here are our current and voltage traces from the amplifier, and here what I did is I used the DAC outputs, our auxiliary DAC outputs, to create stimulus waveforms and read them back in on the input channels. So here I would go into a little bit of what this looks like, and so here you could illustrate a little bit of some of the tools that we have available. So in this case here we have a sine wave followed by a chirp, which is an increasing amplitude and frequency, well, in this case, increasing frequency sine wave. And then here we start off with a segment that's a chirp, then a square wave. You could define a square wave pattern instead of just pulses, and followed by a sine wave, and then we have a ramp here. And again, you can make this as complicated as you like. And then here, these are actually the digital outputs. This is digital 0 and digital 1, where I specified patterns for turning on and off. In this case, I was testing an LED light source. So this is some of the things that you could do with the routine editor.
Okay, thank you, Telly. Here's another one. Can a paradigm include eager function?
Yes, it can. Actually, I think you're still showing my screen here. Right, so you can, one is a paradigm here are commands that are available, and one of them that you can specify is using the execute command. And the execute command basically allows you to go in and use and execute commands that are available in Igor, either commands that were added as an XOP or commands that are native to Igor functionality. So for a paradigm, when you create your program, you have a set of predefined commands that you can work with.
Okay, thank you, Telly. Let's see next question. Can I keep information about the pool parameters or the glass used to make the electrodes?
Yes, Telly, you're still showing. Can you go to set metadata?
Sure.
And okay, you're going to have to go to the preferences and set the complexity level all the way to 3. Sorry about that.
Yep. Okay. Or data, set metadata. Here we go.
Okay, and here in the electrode section,
electrode. Yep.
we actually have all sorts of parameters, starting from an identifier that you can assign to the glass material, which could be borosilicate, aluminosilicate, quartz, something like that, the ramp test value, the puller manufacturer, which in many cases is going to be a Sutter puller, the taper length, whether or not it's been fire polished. What we tried doing here in the greatest complexity level is give you an opportunity to store as many parameters as possible. We do not expect anyone to fill in all 500 parameters at any point in time. But if there is one parameter that you want to keep track of, we want to be able to provide it. And the architecture here is designed in a way that allows us to add parameters that come up as users request them.
Thank you, Yang. Here's another question. We use an 8-volt perfusion system. Can we control it from your software?
Okay, I will take that. So there's two different ways you could do that. You can do it from the IPA control panel, and if you go through the I/O here, you could actually set each of these valves manually, depending on how it's connected. We don't know which perfusion system you're talking about. Some of them need digital outputs for control, or others can be set by using a DAC voltage. Some of them like 1 volt increment for valves. So you could do that both with the IPA control panel, or you could do it directly from the routine editor if you want it timed and synchronized with your main acquisition. And if you do that, then you would then allow, for example, in my multi-test routine here, you could enable digital outputs and then create a waveform. So for example, like in this one here, if you go to the waveform, it was a square wave that I generated for 100 milliseconds. So you could see here that the valve opening, in this case, it's only one valve that would be opening and closing at predefined intervals, but you could also define multiple steps and multiple valves through this. So you could have it either asynchronously through the control panel, through a routine, and one additional place I didn't mention is the paradigm editor as well has commands that will allow to set digital and set DACs themselves through part of the programming as well. Actually, they're currently not implemented here yet, but it's in the works.
Here's another question. Can pCLAMP data be imported or exported?
Okay, I think I should be taking that. That is something that we have not implemented yet. We are working on importing and later on exporting pCLAMP data. The ABF format is reasonably well documented, and a number of people on our team obviously have experience with this data format. There are existing XOPs that allow you to import pCLAMP data into Igor. The challenge here is making sense of the metadata, of the data that are not directly associated with samples and sweeps, and getting them into the context of SutterPatch experiment. If you remember the slide that I showed you about the data structure, the pCLAMP ABF file is the level of what we have as a routine. So all the context within a paradigm, within an experiment, all this needs to be taken care of outside the software. It's not information that's directly associated with the data file. So that's going to be the challenge in being able to import ABF data. Exporting ABF data, similarly, there's a couple things that need to be written. But this has a fairly high priority on our list of things to do.
Okay. Here's another question for Telly. Does the IPA have lock-in functionalities?
Not yet. This is something that that's been discussed and will go into development later on, but currently we do not support the lock-in.
Okay, thank you, Telly. Here's another question. Why can't this amplifier do single-channel recording? The reported noise doesn't seem to be an issue.
I'm going to take that one. It's not like the amplifier cannot do single channel recordings at all. Single channels come in a variety of sizes, and I personally have recorded from some that seem to have a couple hundred picosiemens in conductivity, and that's pretty big. The question is similar to asking, why can't you take a Honda Civic racing or something like that? It's been proven, yes, you can. You can very well take it racing. There's a good chance that there are certain single channels that you can record with the IPA. We do not want to market it as a single channel instrument though, because it does not have the noise level that you can achieve with a 5 or a 50 gig ohm feedback resistor, for example. With other head stage feedback circuitry, you wouldn't end up with an RMS noise level of a factor 20 to up to 100 lower. That is the theoretical maximum where you run into thermal noise. But keep in mind that the moment you put on an electrode holder, for example, all these noise specifications, which are generally measured open circuit, are hard to achieve anyway. And the moment you put a filled pipette into the holder, put it in the bath, then the noise level is going to be a whole lot bigger in those ultra low noise single channel instruments. An amplifier that is a true single channel instrument is in the pipeline, will be coming hopefully sooner rather than later, but we can't commit on a timeline right now.
Another question for Yang. Is activity being logged while an experiment is going on, like electronic lab?
Yes, activity is being logged in the log window. I did not show you much of that. Maybe I should quickly do that. Give me 1 second here. And the log window, I had that hidden during the live session. Things like data acquisition is going on. The paradigm was started. Data acquisition was started. Here is when I recorded the data shown in this experiment. This is a window that allows you to do a free text search. For example, if we look at everything that's associated with bow tie here, this will be highlighted with the bow tie test. You can have a filtered view, things like that. That is an efficient way of letting you find data for now within one experiment, and going forward, the idea is making this searchable across experiments.
Okay, here's another one. Cardiac cells, they can go beyond 100 picofarad. Any chance of adjusting for rather large cells? On Axon 2B, we used to change capacity in the head stage.
Right, in the Clamp 2B, that was the capacitance in the head stage that was changed. That's a question actually that was brought up a little while ago, and we're looking into whether it's possible. It should be possible to handle a little higher, up to 150 or 200 picofarads, with a slight reduction in the range of the amplifier. We have not had a chance to do a proper testing of that yet, which is why we didn't have it on the slide, but that's a very important question, and thanks for asking it, because I meant to mention that and then completely forgot about that.
Okay, thank you, Yang. Here's another one. What pipette holder fits the head stage, Heka or Axon?
So, Jan, you going to take that, or should I?
Why don't you take that?
Okay, so the pipette holder is basically similar to the Axon holders, but these are actually manufactured by, the ones that we provide with the IPA are actually manufactured by us and tested at Sutter. But they are similar to the Axon type, the Axon style. It's not a BNC like the Heka.
And they should be compatible. We don't have extensive testing in cross-compatibility yet, of course, but they should be compatible and they're interchangeable.
Okay, thank you, Yang. Here's another question. We already have Igor Pro 6. Can we use the lesson that we have with SutterPatch?
I think I'll take that one too. Unfortunately, SutterPatch is not compatible with Igor 6. We originally tried doing that, but there were a number of new introductions in Igor 7 that did not allow us to keep SutterPatch compatible with Igor 6. SutterPatch comes with an integral Igor 7 license that is part of the product, but then again, keep in mind it's part of one bundle, the IPA, amplifier, digitizer, and then the software.
Okay, thank you. Here's another one. I would like to see the routine information used in my experiment. Can I do that?
Yeah, I'll take that one. Yes, you can. It's actually part of the data navigator. Jan, would you be able to switch over to live mode? It's good to show that.
You want to look at the data navigator, you said?
Yes. Data navigator, we could show from your example that you had earlier. That would be fine.
Let me give you keyboard and mouse control. Give them 1 second. Okay, you should be good to go.
Okay, so here, for example, we click on one of the paradigms that we stored already. We see here that the routine R8 IV was used. So if you select that and you right-click on it, you have now the option called View Routine. And when you do that, it will open up another panel that will give you an overview of the routine that was used for that particular routine. So here are all the acquisition and routine parameter information. As you scroll down, you have all the input channels and output channel information, and of course you have preview shown. Now, from this, you could actually copy this routine to the pool. This could be quite important for somebody who's sharing data. For example, you got an experiment from a colleague and you're interested in repeating what they did. You could copy this routine to your current pool, or you could activate it and run it directly from here. So yes, you have access. You always have access to the routine information because it's stored along with the data.
Thank you, Telly. Here's another one. Which real-time analysis do you provide other than the shown IV plot?
Telly, I think that's for you too.
Yep, okay, so that I guess is going back to the routine editor to the, let's see if we could bring it up here. Let's go to acquire data. So we go into routines, and it's part of the measurement. In the real-time measurements and graphs, you have all different types of analyses that you could perform. So you select analysis you want to perform, you create your region that you're interested in, and then you could specify graph what X and what Y. And this is not only just from the measurement, but you could actually type in any type of equation that you would like to be shown on the analysis. So it's pretty flexible. You could design any number of different analysis results with this.
Maybe we should also pass that question back to the person who asked. What real-time analysis specifically would you like to see? Because that's very important for us. We are now at a stage where we have a lot of ideas what else we could implement in the software. But of course, we need feedback from the users to prioritize our resources and implement those things that are most important first. So we are very open to getting feedback from users or prospective users. What would you like to see? What would you like us to make?
Oh, one more comment on this. Also, keep in mind that you have the full functionality of Igor Pro to use. So Igor supplies tons of functions that you can have access to, and since all of our data is Igor waves, you have instant access without any export at all to run any type of customized analysis that you like.
Okay, thank you, Telly. Thank you, Yang. Here's another one. Can I recording configuration parameters like cell compensation, series resistance? Can these be saved throughout the experiment to keep an eye on the recording qualities?
Okay, so you could define measurements that don't even have graphs associated with it, and that measurement information will be stored. You could also plot it if you like. And through the paradigm, you have access to all the controls of the control panel, including reading back information like the information regarding electrocompensation and so forth. So you can probably write a paradigm that will put this information into appropriate variables which can be stored. Haven't looked into it too much to actually have an example for you, but there are ways to definitely do this.
And one thing, if you don't need the continuous time course of any changes, any change that you make in the settings is logged to both the metadata and, if you decide so, to the log window.
Okay, thank you, Telly. Thank you, Yang. Here's another question. You have demonstrated through using a Mac system. I assuming it will be all the same on the PC, or are there any difference in functionalities depends on the system?
I could take that one. Absolutely not. I run both a Windows and a Macintosh system here, and the real power of Igor Pro, and it goes back to, God, as long as I remember, them having both a Mac and a Windows system, everything was always quite compatible. So other than a few differences in the way some of the controls look, in terms like, for example, here, the blue coloring on the set variables compared to the gray in a Windows system, everything else looks and behaves exactly the same. There is no advantage or disadvantage with using either system. And we support all the systems that Igor Pro supports, which for Igor 7 is currently Windows, I believe it's Windows 7 and above, and Mac OS.
64-bit, yeah.
Yep. Oh, yes, and that's the other thing. Everything is 64-bit, and everything that we've done is 64-bit as well. So from Windows 7 and Macintosh from 10.9 and above.
What we should also say is, as of pretty recently, like 2 weeks ago or something like that, data acquisition also works on a Mac. Originally, we had to push that back a little bit, but that, thanks to Telly, Hubert, and Greg, came together faster than we anticipated. So now, for both data acquisition and analysis, we can support all systems. And it was really interesting to see the development cross-platform. Part of the team works on Windows machines, part of the team works on Mac machines, and most of the pitfalls or hiccups are things like user interface design, with controls being a little bit out of place, with the alignment here a little out of place, but not so much with the functionality. We've seen very few issues where there was operating system compatibility issues with the actual functionality. I think we should wrap it up at this point. There still seem to be a few questions coming in, and I would say that we address the rest by email. We will leave the session open for a couple more minutes so that anybody who's typing questions right now can continue typing them. Thanks a lot for your interest. Very few people dropped out during the Q&A session. We still have almost everybody there who was there for the entire talk. We realize we ran over a little bit. Thanks a lot for your attention. Thanks a lot for being here today, and stay tuned for the link to the recording.